speaker, Rambod Mojgani, who uh, is very recently joined our group at Rice as a postdoc. Rambod received his PhD from University of Illinois Urbana-Champaign in aerospace engineering, where his work was supported by computational science and engineering fellowship. His thesis has focused on a number of interesting problems in convection-dominated fluid flows, and he has done some very nice work on reduced order modeling of these kind of complicated fluid systems. And we are very happy that he's here today to tell us about some of his PhD work.
Thank you, Professor Hassanzadeh, and thank you everyone for joining us. I'm really delighted to be here presenting my work today. As Professor Hassanzadeh mentioned, I've recently joined Rice, so it would have been perfect if I could be there in person and get to know everyone. But there we go, we are here now. From some logistical point, I have shared my slides on this GitHub page. So if you prefer to just download them and follow through the PDF of the slides, please feel free to do so. I'm going to have them uploaded until midnight, probably, and then remove that. I'm going to be presenting my PhD thesis, which was done with collaboration of my advisor, Professor Playevich at Aerospace Engineering at U of I, and that is on reduced order modeling of convection-dominated flows. And I'm going to address two problems. One is dimensionality reduction, and briefly talk about the stabilization. I won't go through the details of the stabilization part. So I'll start with introducing some fundamentals of model order reduction, then bring up a motivational problem, and discuss the challenges of this motivational problem, which is a convection-dominated flow, and then propose my method on identifying a manifold on which our reduced order model can be built efficiently using a physics-aware, low-rank registration-based manifold learning that we propose. Then I'm going to be constructing reduced order models on top of these manifolds. And of course, I'm going to introduce what reduced order models are in the fundamental section. And then finally touch on the subject of stabilization. Many of the physical phenomena that we are interested in are governed by partial differential equations. And for past half a century, we have been solving them numerically. And it's true that the computers are getting more abundant and more powerful than ever, but still there are use cases that we have to have some low-cost models. So we cannot solve our high-fidelity models for many of the applications we have in mind. One application is the in-situ real-time calculations. Imagine you have an aircraft and you want to solve the equations of the fluid flow over that at the same time as the structure equations. So there's fluid flow and the structure interactions. And you want to make sure at the time of a deployment of a weapon, you can decide if it is safe or not. So to solve this huge problem on a small CPU, which is on board on the aircraft, you probably need to have some low-cost models. Another sets of applications include optimization or uncertainty quantification problems when we have to run our simulations for multiple times, sometimes thousands of times. And these are problems which are called many query applications. As an example of a UQ problem, imagine that you are going to follow a hurricane coming to the Gulf, and you want to track and predict the path of the hurricane moving toward the Gulf. But there are uncertainties in the problem and in the parameters and in the forcing on the weather model. So you probably have to run your simulations for thousands of times. So with a good probability, you can decide if you have to alert the students using Rice alert system or not. So for this case also, you need to have some low-cost models to perform, to have a good estimate of the uncertainty on the quantity of the interest. So projection-based reduced order modeling is one mathematical way of coming up with these low-cost models. Projection-based reduced order modeling also provide us with some intuitions about the fluid flow. That I'm not going to get very deep on that, but that's the subject of another talk. So what are the assumptions of projection-based reduced order models? I start with these and then follow up with how to build these reduced order models. The first assumption is compression. We are assuming that the solution of the governing PDEs lie on a manifold of significantly lower dimension. That means a solution can be approximated, can be constructed using a few number of the bases. So we have turned our system of many degrees of freedom to a smaller numbers of degrees of freedom. And that's called the compression level. In the next step, we are assuming that these manifolds can be trained offline using the training simulations. So we have to run our simulation in an offline phase for a couple of different parameter range or time steps, and then identify this manifold with some approach that I'm going to be discussing. And then we are assuming that these high fidelity models, or PDEs, can be reformulated with respect to this new linear manifold. So this phase is training of our reduced order models. And finally, at the last assumption, we have invested so much in the offline phase, we are hoping to be able to have the reduced order models, which is capable of delivering the solution with a fraction of the cost of the high fidelity models. So the investment we made finally is going to pay off at this stage. So how to do that in two simple slides. We need to run our simulations, the high fidelity models, and we have our solutions. So we can stack the solutions in a matrix here, M, of size n by k. So W is my state variable, and W1, W2, W3, and so on are the state parameters as first, second, and third, and so on. Time steps or time parameter. I stack them together and form a snapshot matrix. Then the low rank approximation problem is defined as minimizing the Frobenius norm distance between M, my snapshot, and M tilde, the reconstruction, the approximation. And rank of this M tilde matrix is equal to K. To satisfy this rank constraint, we can minimize over U and V. So U here is my special basis, a tall and thin matrix of size N by K, and V is a short and fat matrix of size K by K. So I have decomposed my approximation M tilde into two bases, one special basis U and the temporal basis V. And the solution of this minimization problem is simply known from algebra, linear algebra, to be the solution of a singular value decomposition, or POD, proper orthogonal decomposition. So at the end of this stage, I've learned my manifold, I have learned my bases that explain my manifold, I have learned the manifold on which the bases span. So I'm going to now be constructing my reduced order model on top of this manifold. Consider these residual equations R of W at time step n equal to 0. This can be representation of a discretized system, or it can come from discretizing a continuous system. And this is a system of size n. Then I assume that my state parameter, W, can be approximated on the global trial subspace. So W is approximated by linear composition of U and WR. So you remember from the previous slide was a tall and short matrix of size n by k, and WR is the state variable on this reduced space, on this manifold, which is size k. And I'm assuming k to be much smaller than n. For Galerkin project, so I substitute this approximation in my residual equation. So substitute W with UWR, and then project that to the test subspace U here. in a Galerkin projection. You can use Petrov Galerkin, but let's not discuss that here, just Galerkin projection. And through this procedure, I have turned a system of size n, equation 4, to a system of size k, equation number 6. So essentially, we hope that solving this equation number 6 to be much more efficient than equation number 4. And we gain a speed up through this procedure. But I skipped somehow some main principle assumption here, which was k can be chosen much smaller than n. Now you might ask how accurate this assumption is, which is a fair question to ask. So let's check that with a very simple problem, a scalar linear convection equation, and see if that approximation is actually a precise and accurate enough assumption here or not. So partial w partial t plus partial w partial x equal to 0 on a semi-finite domain, the x between 0 and infinity, and at time 0 to 1 with a Gaussian initial condition and a fixed endpoint boundary condition. You know the exact solution to this problem. It's just the Gaussian moving to the right of the domain, right? That I have simply plotted here. So in the bottom, I have w, my state variable, versus x in different time steps, time 0, time 1/3, time 2/3, and time 1. And I have my snapshots on top. So on the xt domain, this yellow line moving to the right side of the domain, this represents this Gaussian moving to the right of the domain. So having these snapshots, let's perform SVD on that and keep 5 of the bases. And I end up with column B of this figure. So this is how the approximation works. You see that the solution, the approximation or the reconstruction is not very close to the exact solution I had in mind. There is non-physical diffusion in the domain. There's non-physical oscillation in the domain. And you might at this point doubt my assumption of k being much less than n, which is a correct doubt to have. Of course, by adding to the number of the bases, the solution, the approximation gets closer to the exact solution. But with such a simple problem, you might have expected a better compression efficiency. So this was a partial differential equation and solution of that itself. But that's not the only place that you see this problem. This problem is more general than partial differential equations. I just chose some problems from machine learning or computer vision problems. My snapshot matrix is now comprised of images. And so the first column of this matrix represents this image and so on, representing a 90-degree rotation of this character A. So again, I have my snapshots, I perform SVD on that, and I keep one of the bases. And let's plot them here. And you see this rank 1 reconstruction of the solution, this POD subspace that we realize is not accurate. You can't even see the rotation on this subspace with one basis. So I hope with these two problems, I have convinced you that there are problems that simply cannot be approximated using a small number of the bases, using this traditional linear approach. To generalize my statement, it's simply not possible to efficiently compress some of this wave-like solution using a low-rank decomposition. By wave-like, I mean a traveling feature in the domain, like a traveling surface, traveling interface, traveling shock, traveling gradient. And we need to have a fundamentally different approach to address this issue. And this has been known for 20 years, and people have been coming with different approaches to address that for the past 20 years. In the first category of the approaches, we seek for self-symmetries, symmetries, some kind of coordinate transformation, or we modify the decomposition, the minimization problem, if you remember. to include these properties. In the other sets of methods, the idea of global bases or global domain is foregone, and local bases are used, or the domain or the bases are split. And lastly, in the last category of the methods, the temporal dependency is added to the bases. So the idea of having different set of bases for the spatial and temporal properties are foregone. And our spatial bases in this case are time dependent. So we are proposing to construct our reduced order models on a nonlinear manifold, and we want to keep some of the proper ideas from the previous approach, but address some of the inefficiencies of those approaches. First of all, why do we even care about the linear subspaces in the first place? We saw that they are not very efficient, but they're still commonly used. Why is that? The main attraction of those approaches is that they are interpretable for us. For example, in proper orthogonal decomposition, we can capture the most energetic bases of the domains. And there's the idea of the coherent structure, and we can interpret and understand or flow fit with that. Or in dynamic mode decomposition, we approximate our nonlinear system with a linear system of reduced order, and then we can perform all sorts of linear LTI systems, linear time invariant system control under our system. So they're useful, but they are not very efficient in compression, as we discussed. On the other side, from machine learning society, they learned that this compressibility is an issue and came up with nonlinear manifold learning problems. ISOMAP, CSNE, neural network autoencoders are some of these approaches. But when they came up with these approaches, they were not very concerned about interpretability of the method. So we don't have the advantages of the linear subspaces that we often use. Also, not many of these methods were concerned about projecting back the solution from the reduced order, from the learned manifold to the physical space. So what we are looking for here is to keep the interpretability of the model, but gain compressibility. So I'm looking for an approach which is data-driven, like all of these methods. It's efficient in its compressibility, like nonlinear methods here I showed you, but I want to have a map between the latent space, the manifold that I learn, and the physical space, the manifold that I work with, that I understand. And I want these latent variables, or the map at least, to be interpretable and have some physical meaning. So that's why we came up with the idea of physics-aware low-rank registration-based manifold learning map. I've tried to show everything in this single slide. In the next slides, I'm going to just formalize that and put this one slide into math. So this is basically what I want you to take home from my presentation today. On the left, I have my grid in X and time. You see that? It's uniform, but it doesn't have to necessarily be uniform, but traditionally it's constant in time. That's an important point to have in mind. And I have my snapshot matrix, M, of size n by k, on top of this time constant grid. And by constructions, this is high order or high rank, which is the case for convection-dominated flows. As I motivated in the previous slide, I'm looking for a map. Here I call it G. And I'm looking for a manifold on which my solution is low rank. So I can express my solution on this identified manifold using a few number of the bases. That was the whole point of doing model order reduction. So G is a function, or is a map to be precise, that takes the solution, my snapshot, from this time constant domain to an abstract manifold on which my solution is low rank. And G inverse is, of course, the reverse of that. G inverse takes my snapshot, which is built on this length manifold, to the physical space M. And I tie this idea of the mapping between these two manifolds to grid, to a time-varying grid that I have plotted on top right. And furthermore, I assume that this grid, this time-varying grid, is low rank. So I can represent that with UX, VX. UX is going to be the spatial basis of my grid, and VX is going to be the temporal basis of my grid. And by construction, I assume them to be low rank. That gives me some nice properties. With this having in mind, G can be seen as simply as interpolating between this time constant grid and time varying grid. So let's formalize this. I'm minimizing the distance between the snapshot M and G inverse of M tilde. I'm looking for this map, so I'm minimizing over G here at an abstract level now. I haven't given you a recipe of how to find G at this point. But I said I want M tilde to be low rank, so I can substitute M tilde with UV here. And UV, if you remember, comes from the minimization problem I showed at the beginning of the talk. And also I'm assuming the grid to be low rank, so I replace G with these grid bases, UX and VX. So my minimization is now over the UX and VX. So the solution of this minimization problem is going to give me the basis of the grid and therefore the grid. And at this point, G is simply an interpolation between time constant grid and time varying grid. So this is the whole manifold learning problem that I proposed. There are some more points that we should consider, and that is this map should be diffeomorphic. That means I want G and G inverse to be differentiable. That provides me with some guarantees. This assumption guarantees that M tilde is unique and exists given M and vice versa. And for my map to be diffeomorphic, I need to satisfy two properties. First, my map should be bijective or one-to-one, and it should be smooth. And to enforce bijectivity, I can make sure that there is no negative cell volume in my domain. So all my grid points, grid cells have positive volume. And to enforce the smoothness, I can penalize any abrupt changes in the grid spacing in space or time. So I have included them in the minimization problem that you saw before. And these blue points are going, these blue terms are going to provide to enforce the diffeomorphism. Gamma 1 UX, the norm of that, and then VX gamma 2 transpose norm of that is going to penalize any abrupt changes in UX and VX. And also I can constrain my grid volume to be positive. Also, usually we are interested to keep the boundary points in place so they don't change in time, they don't move in time. I can add that as a constraint to my minimization and solve for the grid points. So let's now go back to the problems that we started with. You remember these snapshots of a rotating character A, and you saw that POD wasn't very efficient into reconstructing that. Now let's solve the minimization problem, which means I'm looking for the grid, and that's going to look like this. So here I have plotted the rank 1 grid corresponding to this identified manifold, and you see they're rotating. And if I plot my solution, my rank 1 reconstruction on top of this grid, is going to look like the figure D. And compare that with the snapshots and panel B, and we see that this reconstruction is much closer to the snapshots compared to the POD subspace. You might see some shear in the image in the reconstruction and some scaling, and you might ask why that happens. And I can tell you that's because the rigid body rotation of the snapshots cannot be represented on a rank 1 grid. So increase rank of the grid from 1 to 2 and solve the minimization problem. That's what I've done here. plotted in figure C is a rank 2 grid corresponding to this identified manifold. Now, if I plot my reconstruction, here again, the rank 1 reconstruction on this grid, the solution is much closer to the snapshots. So how about the partial differential equations? After all, we are engineers and we are interested in that. So here I have done the same procedure for a second order wave equation with a Gaussian initial condition and a fixed endpoint boundaries. On the left, I have the Eulerian grid, and on the right, I have the rank 2 grid, the solution of my minimization problems. So this shows you how the grids move in time. Now I plot the reconstruction on top of this grid, both rank 4. On the left, I have the rank 4 reconstruction on the Eulerian grid. On the right, I have a rank 4 reconstruction on this time varying grid. And you see the time varying grid and the reconstruction on top of that is much more accurate. Of course, again, with adding to the number of the bases, the solution is going to be much closer to the exact solution I had in mind, but still you see that what I could get with rank 4 reconstruction on this time varying grid is even more accurate than the Eulerian grid. To be more precise, I've plotted the error, so the difference between the snapshot and this reconstruction versus the number of the bases, so the size of the reconstruction in this plot. Dashed blue line is the Eulerian case, and this solid black line is this time varying reconstruction error on this time varying grid. And you see my model is much more accurate compared to the Eulerian case. That shows better, more efficient compression. Now let's be a bit more complicated. I have chosen Euler's equation, 9 linear equations in viscid fluid equation. I have stabilized that using high order artificial viscosity and assumed perfect gas, and solving that problem for this initial condition on the left. So the solution on different time steps looks like what you see in figure B. Again, let's look at the snapshots and the Eulerian grid and the rank 8 reconstruction on top of that, the time varying grid. So this is the time varying grid at the last time step that I'm interested in, and rank 8 reconstruction on top of that. And you see the solution is much closer to the snapshots on this time varying grid. On the bottom, I have the line plot of the diagonal of the domain. It should be obvious from the top row as well. This thick gray line is the snapshots that is behind all the other two lines. This dashed blue lines corresponds with this Eulerian grid, and this red line corresponds to their time varying grid. And you see the reconstruction on top of this time varying grid is much closer to the snapshots. So up to this point, I have built the reconstruction for the density. I showed the results for the density, but of course, if you look at the pressure, velocity, and density, you will see the improvement I get from this time varying grid. So again, here, the dashed blue line is the Eulerian case, and the solid black line is the time varying case. Up to here, I showed you that for this convection-dominated flows, you need another approach, and showed a low rank grid can be identified that can efficiently compress or reduce such as snapshots. To put the method in another words, I propose an approach that efficiently registers the output sequence of the PDEs on a low rank time varying grid. This representation of the method is going to be more familiar for the people who are familiar with image registration and machine and computer vision tasks. So up to here, I have built the reconstruction. I have showed you the efficiency of my compression, but I haven't yet constructed the reduced orders on top of that. So the second slides, I showed you about the projection-based reduced order models. So let's get to that. I want to look at this problem from two different perspectives. In the case that you have the governing equations, you can perform projection-based reduced order modeling, what I showed you before. But there are cases that we don't have access to these governing equations. That's the most compelling reason to use approaches such as system identifications or neural networks such as RNN to construct a model on top of these manifold. Note that these methods are not simply reduced order modeling. They can be done on the high dimensional physical spaces, or they can be done on the reduced space. Here I'm going to just focus on the building them on the reduced space. But they are more useful when we don't have the access to the system of equations. So let's first start with the projection-based reduced order models. And you remember this slide from previously, and we changed this minimization problem to the low rank registration-based method. So we have to change how we are constructing our reduced order model. And what changes here is basically the approximation. I'm substituting this approximation on the Eulerian grid with the time varying basis approximations. So the state parameter at time step n is approximated by using the basis at time step n and the reduced coordinate system, the state variable on the reduced coordinate system WR at time step n. And basis at each time step is just G inverse of the basis at that particular time steps. So substitute that basically onto the residual function, project that onto this trial subspace, and we get this equation 22. And that's going to be a time varying system of equations. And that's my ROM. So again, let's go back to the Euler equations that you saw before and make sure our reduced order model can actually produce the same results as the high fidelity model. So the same initial condition, see the snapshots again here. And the snapshots, Eulerian grid and rank 80 comes a solution of the ROM here, and rank 2 grid and the solution of the ROM on top of that. Note the difference between the previous slide I showed you that was similar to this but different. That was reconstruction. Here we have the ROM. And on the bottom, I have plotted the solution on top of these different manifolds. So this thick gray line behind all of the lines is the snapshot. This dashed blue line is a reduced order model, and this red line is the reduced order model on top of the proposed approach. And if you remember from the previous slide, you see that there are more non-physical oscillations in the solution of the ROM on the Eulerian grid. And that is because of the instabilities that this inaccurate and not efficient compression leads to on the Eulerian grid ROM. So we could gain some much more efficient ROM, more than expected, using this time varying grid. And the error plot versus the number of the basis functions approves that as well. Another problem that I didn't show you before was prediction. So up to here, I was just producing the solution in the regime that I actually had this access to the snapshots. But what happens if we don't have access to the snapshots? Here, let's say I have just solved my high fidelity model within a limited time period between time 0 and 0.1. And I want to predict into future and what happens at the last time step, time 0.25. On the top, I have the snapshots, the Eulerian grid, and the solution of the ROM on top of that, and rank 2 grid and the solution of the ROM on top of that. And the figure BD, I have the line plots, and I also am plotting the transient error versus time for these figures. So this blue line represents the Eulerian grid, error of the ROM on top of that, and this black line represents the time varying grid, solution of the ROM on top of that. And if I extend my simulations into the future for the Eulerian grid, you see that the shock doesn't convect with the flow and it remains stationary, and that leads to orders of magnitude higher error. But in the time varying grid, you see that the shock, this red line actually moves with the convects as it should, and the error is going to be much less than the Eulerian case. So we could do prediction of convection dominated flows using this approach. So that was the projection based reduced order models. Now I want to show you my results for the recurrent neural networks and see how this idea of manifold learning can be used in this framework. Usually an autoencoder is used to find the manifold on which the space is low dimensional, and then a recurrent neural network is learned on top of this manifold on this low dimensional space that represents our dynamical system at the bottleneck. So the system of equations is evolving on top of this green bottleneck of the network. What I'm proposing to do is to precondition the snapshots using the map we learned. So basically having your snapshots have G of M, so have the snapshots on top of this time varying grid, and then perform the same architecture, build and train the same architecture on top of this identified manifold. And my thesis is that this is going to give you better accuracy because you can gain, because you have reduced the dimensionality of your input in the first place using the proposed method and the G corresponding to that. So let's see how it works for a viscous Berger's equations. It is very similar to the convection equation I showed you before, but there is a nonlinear term here, and there's a viscous term here, the Gaussian initial condition again, and the solution on this figure A. If I build my reduced order model, basically I train my network on top of the Eulerian grid, you get the solution of the recurrent neural network as in figure B. But if I precondition my snapshots using the identified manifold, you get figure C. And you see that with the proposed approach, we are much more closer to the snapshots. And to be more precise, I have plotted the error versus the number of the bases in figure. So this dashed blue line is a traditional way of doing neural network and autoencoder and on top of that. And this black line is the physics-aware autoencoder. And you see the improvements. But more importantly, we are interested to see how it does in the prediction regime. So I have run the simulation further from my snapshots. The exact solution is plotted in figure A, the traditional way of doing neural networks in figure B, and preconditioning that using the physics-aware autoencoder is plotted in figure C. And at this point, we gain the convection, sure, but the most important issue is that even by increasing the width of the bottleneck, even by increasing the size of our reduced order models, in the traditional approach, we could never get the prediction of the convection. We could just do that because the convection is already captured by the low rank grid deformation that we solved for a priori. So I showed you how to build ROMs, both projection-based ROMs and the neural network-based ROMs, and I showed you how we can improve prediction in both cases. The last stage of this projection-based ROMs is going to be a stabilization of that. That I said I'm not going to talk too much about them, but we know that these projection-based reduced order models does not come with a stability guarantee in a POD approach. So we have to come up with some stabilizing method. I've proposed a minimization and optimal control problem that tracks the trajectory of the output of the ROM and make sure this is close to our high fidelity models. And that's done by tuning the singular values of the system matrices. I won't go through the details, but you can read more about that here. And with that, I want to conclude. And to summarize what I talked about today, we saw that no reasonable low-rank approximation exists for these solutions with the sharp gradients, sharp discontinuities, moving interfaces, and we find some interpretable manifold learning approaches that can be applied to this method, and we can actually gain prediction using this proposed approach. And then we can finally build the reduced order models on top of that, which is going to be time varying systems, and we can actually stabilize that. And with that, I want to thank everyone and ask the host for taking the podium.
Okay, great. Thank you.
Thank you.
So, yeah, so we have time if anyone has any question. So again, yeah, you can raise your hand, or and I can unmute you, or you can just type your question in the Q&A. So one question, when you talked about the instability, so physically, where would the instability come from? What's the physics of the instability in these kind of problems?
Actually, there's a big dispute about that. There is, for the convection-dominated flows, there's one line of thought is that we are removing the low, the high frequency, low energy parts of the system. So we are actually removing what is going to cause diffusion. And truncating that part is going to make our system, which was diffusive in the first place, not diffusive. And that's going to lead to instabilities. But there are some other line of thought that is arguing that's not all the story, and actually the diffusion cannot explain all the happenings, all that happens in the domain. So the argument is still going on. I've seen paper as late as this summer on that.
Okay. 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 Anyone in the audience is there any questions for Rambert?
I can't find the question, so if
there's no question currently in the Q&A.
Okay.
So if you want to apply this approach to a more complicated flow, so you applied it to the Berger's equation, but if you want to apply it to flows that are multi-scale, would it work? And what would be the challenges in doing something like that?
So the first challenge I have is an implementation challenge. So I'm doing everything on CPU, and I need to interpolate my system on this grid. And this is a very costly optimization problem to solve on the CPU. But luckily, you can do interpolation on GPU like very easy. So if there is any undergrad students that want to code that, please reach out. So that's the first issue that I need to solve. But from theoretical standpoint, multi-physics. So do you have an example in mind? What exactly your problem
I'm talking about multi-scale. Mm-hmm. So if you so you have the shock wave, which has a strong nonlinearity in some locations, but it's not a very multi-scale flow, right?
I see,
but on the other hand, if you look at even like a force Berger's equation, or if you look at like a 2D turbulence flow, or any real turbulent flow, then you will have all sorts of scales in the problem. So I'm just trying to figure out these maps that you find.
Yeah.
Then you have a multi-scale system, how they're going to evolve and what's going to happen.
So the main problem that's going to occur is the same as any other ROMs. So this is not specific to this ROM. You are truncating the high frequency, lower energy part of the system. So you are removing diffusion from the system, and that's going to lead to instabilities. That's going to be even a harder challenge in the multi-scale problems when you are basically need many more bases to represent the solution. But again, we are addressing some part of that problem by being able to have the same accuracy using a small number of the bases. But I would imagine that still the system is going to be unstable and you need to add diffusive term in that or do another stabilization method on top of that.
Okay. Okay, great. So there's one question. I don't know, can you see the question or?
Let me see. Yes, Ricardo is asking, how much is the computational time reduced with this approach? So I didn't specifically talk about the computational cost benefit of this approach because there is another step that needs to be done if you want to gain computational speed up in the nonlinear system of equations, which are the systems that I am interested in. For the linear system of equations, you can compute the bases appropriately and save them somewhere and use them, so it's going to be RAM intensive. But in the nonlinear case, you need to evaluate the nonlinear term. There is a way to get around that though. You can do time on that, or you can do hyper reduction and save some of the computational costs on that. But I haven't implemented that, but that's a necessary forward thing to do.
Unmute. So what does DIME do?
DIME basically selects some points from your domain and do an approximation of the domain from those selected points. So now instead of computing f, your nonlinear function on all of your points, you can compute the nonlinear term on those time points and then reconstruct the nonlinear functions using those single points. So instead of having to evaluate the nonlinear function on all your points, you can do that on the time points only and gain the speed up on that.
Okay, great. Okay, is there any other questions? Okay, great. Well, let's thank Rambod. It was clapping on behalf of everyone, and hopefully you will move to Houston soon, and you'll see everyone.
Thank you. Yeah, I really like to see everyone in person.